Hello, this is Jonathan Doolin, and I'm working on a project. I don't know how far this is going to go, but I want to correct confusions in special relativity. Okay, and there seem to be a surprising number of papers written just to argue against the special theory of relativity, and many of these are published. And I'm not really an expert on what journals are respectable and what isn't respectable, and there's probably a lot of disagreement on that issue anyway. What seems surprising, though, is that there isn't any central resource that acknowledges the hypotheses of these papers. A lot of ideas, whether conceptions or misconceptions, are surely repeated in the different papers, but there doesn't seem to be any effort made to categorize or correct them. There seem to be essentially about three varieties of criticisms, and one of these, there are internal inconsistency, experimental failure, and just ignorance. An internal inconsistency of a theory is like a self-contradiction in the expression of the theory itself. If you try to express the theory and then you realize that at some point you're saying you can realize that you have a reductio ad absurdum argument that can be made to identify that your theory doesn't really make sense. Another problem, it could be meaninglessness, where perhaps at some point during your argument you are using words that you have not necessarily defined and you don't even know what they mean, but you're just repeating them. Um, and so that could be a problem with your theory. An experimental failure is one where uh, once you can't really have an experimental failure um, with once you have a theory that is not self-contradictory or meaningless. um, I'm sorry, if you have a theory that is self-contradictory or meaningless, then you can't say that the same theory has had an experimental failure, because if you have an experimental failure, that implies that the theory that was being promoted makes enough sense to fail an experiment. Um, so if you have an experiment has been performed and the theory failed, it means that the theory was internally consistent. You can't have an internally inconsistent theory really fail an experiment. Um, okay, and then a third criticism is maybe you don't know because you don't have the data to support your claims. Um, this happens as a criticism quite a bit too. If somebody is over here trying to explain a theory to, to describe this part, and this was often what happens in the arguments, is that you might be defending the consistency of a theory, um, and somebody else comes along and says, you don't really know if you're right because you don't have the data to support your claims. And it may be true. Honestly, I have never been in any particular environment where I was able to really test all of the ideas behind special theory of relativity, because I don't have any means to go near the speed of light and set up clocks or anything like that. It's all uh, Gedanken theories, um, experiments of the mind and stuff like that. But I don't have the data to support the claim that the special theory of relativity is experimentally correct, but I do have the knowledge of it to say that it is internally consistent and it is meaningful. So in regards to the internal consistency of the special theory of relativity, I have essentially zero doubt that it is internally consistent. Special theory of relativity is nothing more and nothing less than the application of hyperbolic trigonometry to space and time. Now, regular trigonometry is the equation, basically goes around the equation x squared plus y squared equals r squared. You'll notice you'll have a center and you'll have x squared plus y squared equals r squared with the radius of each circle. Every point on that radius, if you put that center of the circle on that, if you put that center of the circle at the origin, then every point on that circle satisfies this equation. Hyperbolic trig, on the other hand, is the form either x squared plus y squared equal x squared minus y squared equals r squared, or y squared minus x squared equals r squared. In the first form, we can draw something like this, and we have x being the larger magnitude number, and the I should draw like that, and this. They're hyperbolas. This is the equation of hyperbolas. Y squared minus x squared equals r squared is the set of hyperbolas over here. And so if I replace one of these variables with, let's say, the y, with the quantity c times t, then we have something like a space-time diagram with ct going this way and x going this way, and ct going this way. And this describes events, describes the location of events in the future and the past, and this one describes events that are to our left and to our right. Now, what we can do with these things is, one of the things we can do with this one is we can rotate the diagram. And the situation of x squared plus y squared is conserved as long as we rotate it around that center 0, 0. The same thing happens with the hyperbolic trig. Well, actually, let me show you the rotation diagram. It goes y prime comma, no, yeah, x prime comma y prime, I think, equals cos theta, negative sine theta, and sine theta. And this is a rotation clockwise around, or counterclockwise around the origin by an angle of theta. On the other hand, the hyperbolic rotation goes ct prime x prime equals, and then we'll have cosh phi, I'll put var phi in there, negative sinh var phi, sinh var phi, and cosh var phi times ct and x. And again, this is only a rotation around this origin right here. And what it does is it takes, let's see, I think this is an acceleration to the right. This is looking at things, figuring out what it would look like if we accelerated to the right by rapidity of var phi. So what would that do? It would essentially take the events that are over here in our future and move them to the left, and it would take, so all of everything that is on this hyperbola doesn't move like, it doesn't move like that. It moves down into the past and to the left. If it's over here, it would, of course, if we have this line, it will actually move that way. In the meantime, these lines are all coming this way, so these lines also come this way. So these hyperbolas move down, these hyperbolas move to the right, these hyperbolas move up, basically. They are all moving up. And then these move down and to the left. So again, that direction, if I accelerate to the right, the events in my future move to the left in my point of view, and the events in my past move to the right in my point of view. And then I match up the arrows here, so that comes down, down, and this goes up, up. So it keeps everything together. Now, one thing we can do with this, we could rotate this image around some other center. Like if I wanted to rotate around that point, then it would actually cause the origin, if I rotated clockwise around that point, I could actually rotate that origin, 0, 0 point, somewhere to a different location. Same thing goes with this. I can rotate around this point, and it will cause it to go down, down, up, up. Okay, so it will cause those events to rotate around that point, and that would cause, depending on which side of the event horizon there, or the light cone it's called, which side of the light cone that is on, it's either going to go this way, or if I had drawn the light cone just a little bit above it, it would have gone kind of down in the other direction, stayed in the past rather than being in the present. So what that would look like mathematically is we would just, instead of ct prime here, we would have said ct prime minus t of the boost prime and x prime. And then over here, it's good I wrote it again because I realized I have an error right there, negative sinh phi. Because this one has a negative positive, and you'll see here, if you take the determinant of this thing, you get cosine squared theta minus negative sine squared theta, which is equal to cosine squared theta plus sine squared, and that's equal to 1. And down here you get cosh squared minus negative negative is sinh squared is also equal to 1. So the determinant of both of these matrices is 1, which means something, and I forget exactly what it is. But anyway, when you plug in the other side of this, I should have x prime minus x prime boost, which is the coordinates of the boost. The boost here is the point around which the whole coordinate system is being accelerated, just as the point of rotation here is the point that we would be rotating this diagram around. So there is a location, there is necessarily a center whenever you perform this transformation. You can't do it without kind of describing a center somewhere. So let's continue. T prime minus T boost prime. We plug in T minus T boost. And here we put X minus X boost. And the boost coordinates in the primed reference frame is not necessarily the same as the boost coordinates in the non-primed reference frame. Okay, so this is the article that I'm currently working on. What I'm going to do is actually take this video and put it as a link somewhere here in section 1 after I describe, what is this, the Lorentz transformation. I'll put in a link to this video here, and then I will start discussing J.H. Fields in the next video. In particular, his article called Consequences for Special Relativity Theory Restoring Einstein's Neglected Additive Constants in the Lorentz Transformation. Thanks for watching.